This is the official video for encoding multi-level dynamics in effect heterogeneity estimation. I'm Moran from Harvard College. This is joint work with Connor and Adel from UT Austin and Linköping University. Earth observation data is increasingly used in policy analysis. It's used to link RCT data to satellite imagery around households and villages to improve the estimation of conditional average treatment effects. However, the algorithms generally used in these CATE estimation procedures use images on a fixed single scale. When using images on a fixed single scale, there's a challenge of balancing fine-grained individual level heterogeneity with broader contextual level information. And the key question that we are answering for our research is, how can we effectively incorporate these multi-level dynamics in causal effect estimation, dynamics between me as an individual situated around my household with my broader neighborhood and the information in my broader neighborhood related to my response to a certain treatment? Our contribution is to propose the method multi-scale concatenation, which is a composable procedure that transforms single-scale algorithms to multi-scale ones, and it's easy to use, and we show that it improves the performance of K-estimation algorithms compared to single-scale ones. The intuition for the need of these multi-scale representations can be seen on these two images. This is the house Longfellow's historic site in Cambridge, Massachusetts, and this is the neighborhood around it. Still, the image is centered around this house. Here we have a small-scale image versus a large-scale image. A natural question for us to ask when doing causal effect estimation using satellite imagery is whether the left information or the right information is more relevant for extracting the signals about effect heterogeneity from an intervention on a household here. It's a priori unclear because this image shows more detailed fine-grained household level information about what the houses are like. However, this enables us to discern the whole neighborhood. For example, it shows that there's a river around the house. There are these roads. There are a lot of densely populated places, a lot of trees. So it's hard to say. Therefore, the current approach with single-scale analysis fails to capture these multi-level dynamics as shown in the picture. Larger images provide context, provide neighborhood level context, as in the ones that we saw before, but lose local detail. Whilst the smaller images capture local detail, but they miss broader patterns. The solution that we propose is multi-scale concatenation. We combine representations from images of multiple scales in order to preserve both local and contextual information. The multi-scale concatenation procedure that we propose to do this is composable with existing algorithms, so no deep architectural changes needs to be made in order to incorporate multi-scale information, making it easy to use in practice. In terms of notation, we have units and village level geolocations as xi, and an image extraction function fi that takes in the xi, the geolocations, and some image size in R plus to output an image. And then we have a representation function phi that takes in two images and outputs some representation. And a K-estimation function that takes in those representations to output a conditional average treatment effect estimate. At last, after we have all the K estimates, we use a heterogeneity quantification function mu, and here we use the rate ratio as our quantification metric to quantify the quality of our K estimates. The goal of our optimization, after we obtain a representation function and a K-estimation function, where the K-estimation function can be obtained through standard techniques like meta-learners or generalized random forests, and a representation function can use pre-trained feature extractors, such as different vision transformer variants, or ones that are fine-tuned on satellite imagery, and also using the multi-scale concatenation techniques, etc. After we have this representation function, our K-estimation function, we can maximize the heterogeneity signal that we detect out of the image by choosing the best image sizes within these two scales. And here is the heterogeneity effect that we have detected through images on size 1 and size 2 compared to the baseline where we use a single image scale. The natural question is, well, how do we actually detect these representation functions? How do we construct them? Multi-scale concatenation is the way to do so. This is a single-scale decomposition where the traditional single-scale approach uses a single-sized image M, sends that M through a feature factor phi, and uses those features and combined with some of the previous K estimation functions to get a tau I, the K estimate. What we do instead to construct the phi function is to take in as input two images, MIS1, MIS2, of different scales, S1 and S2. Use two powerful pre-trained single-scale base feature factors, phi IS1 and phi IS2, to extract the conditional average Truman effect estimate. The intuition for why we're doing this is that multi-scale concatenation composes these base feature representation extractors to better approximate an oracle function that takes in an extremely large image and just extracts all the possible heterogeneity signal inside that image. Whilst the traditional approach would miss much of the heterogeneity signal by using this representation extraction function, where much of the signal from multiple scales is lost in this single image when we're doing dimensionality reduction. Because if we have a large image, the features on a smaller scale wouldn't be salient and wouldn't be extracted by phi IS. Because of the difficulty of quantifying the model performance when doing causal effect estimation due to the lack of ground truth data, we employ simulation. The intuition of our simulation is that we introduce perturbations at multiple scales. Here, an image of size 32 by 32 versus images of size 256 by 256 to test our model's ability to capture these signals when we use multi-scale concatenation, as in when we're using the representations from this scaled image versus this scaled image together, compared to a baseline model that uses representations from only a single scale image, either the 32 by 32 or the 256 by 256. What we found is that multi-scale concatenation acts both as a robust estimator and perhaps more surprisingly, a signal amplifier. What we see is that multi-scale concatenation in black can recover most of the information when there are signal at a single scale. But if there are global perturbations of information present at both a small scale and a large scale, multi-scale concatenation can actually even capture that signal better. And this is for when there are separate local and global information together, multi-scale concatenation can also capture both. I invite you to read the paper for more simulation details. Simulation is nice, but simulation doesn't always translate to empirical performance. So we also examine multi-scale concatenation on two RCT data. We have Peru RCT data on a multifaceted anti-poverty intervention from 2007 and 2015, and another one from Uganda, which is a randomized business grants program to young people from 2008 to 2012. And we use Landsat satellite imagery linked to the geographic locations of these RCT units to affect heterogeneity estimation. Here's an example satellite imagery that we have over Peru. Here we have a large-scale image, and we have gradually smaller scale images to test multi-scale concatenation and its performance. What our results find is that there's strong evidence of multi-scale dynamics in Uganda, moderate evidence in Peru, and that multi-scale selections could differ with context and choice of both the representation function that we use, so the base feature factors that we use, and also the application context of what countries there are. There may be different kinds of multi-level dynamics involved. But we see, for example, in Uganda here, the whiter and the higher, the better, since it's the rate ratio that measures the amount of heterogeneity that our model detects. That the best performing rate ratio estimate in Uganda comes from combining an image that's of a very small dimension with an image of a very large dimension. Whilst in Peru, it requires two medium-sized images of slightly different scales. The counterintuitive finding that we have is that having a larger image is not always better. And I think the intuition that just providing a large image and having a base feature extractor take all the relevant signals from that image is always better, is why multi-scale concatenation or other multi-scale techniques have not been proposed before. We have two observations. First, smaller scale images often generate stronger heterogeneity signals, as in the Uganda case that we see just then. And our optimal combination utilizes both small image and medium to large size images to capture the signal from both. This shows that large scale images fails to capture certain fine-grained heterogeneity information that's present in small scale images. Further, larger scale images has higher image overlap between units when units are, for example, in a village, which means that it's much harder for the model to discern the individual level heterogeneity from larger images. The implications of our finding is that there needs to be more careful thought of how to balance local and contextual information. And our multi-scale approach is both simple to employ and provides robustness to local and global information and their presence. In terms of the conclusion and summary of our work, we propose a novel multi-scale concatenation procedure. We find evidence for multi-level dynamics and affect heterogeneity in practical empirical RCTs. And we provide a practical guideline for scale selection through grid search. This is relevant for both policy optimization, but for scientific understanding of the underlying heterogeneity estimation process. In terms of future work, we could extend our work to observational settings, since currently we rely on randomized controlled trials for causal identification. We can also integrate multi-scale concatenation with other dimensionality reduction methods. This is because by concatenating these representations, the dimensionality of our input representations increase, and the performance of multi-scale approaches may increase drastically if we have suitable dimensionality reduction methods before sending it to a CATE estimator. Further, more interpretability techniques is needed to disentangle multi-scale dynamics in images for better scientific understanding of the underlying heterogeneity estimation process. Thank you. For future work, please see planetarycausalinference.org.